and could be the electron or charge separation in an antenna, for instance. The electric dipole is measured or determined as a vector quantity that points from the negative charge to the positive charge. And there are reasons for that. If a dipole happens to be in an external electric field, then the direction this thing is going to interact it'll always be in the positive side, will always be in the direction of the positive field, or the electric field, and the negative will always be in the opposite direction, because it's attractive. So by defining this quantity, well, first of all, why do it at all? Well, if you notice, coincidentally, and this is a plus, not a minus, isn't it? Get my signs there. Coincidentally, both solutions, and really generally all solutions, if one were so inclined to calculate it, as long as d is very, very small relative to the spatial distances, and that's usually the case. Otherwise, there's no reason to treat it as a dipole anyway. It's just two charges next to each other. They are both related to this QD quantity. So it's the common variable for both problems, or for both solutions. So, and since that represents physically something to do with how these charges are separated and the quantity of charge, then we just give this thing a convenient definition. We call it the electric dipole moment, which allows us to say that whatever this vector is, now I've got all kinds of stuff on here, and it's going to be even trickier to write anything extra. I'm going to get rid of this portion for a minute. If we have the minus charge pointing a certain distance of separation into the positive charge, then the dipole moment vector, which is defined from negative to positive, is related to the magnitude of the charges, because again, the assumption is for a dipole that they're equal and opposite charge. It's not 2d and a negative q, or a 2q and a negative q. For it to be a dipole, or effective dipole, you need to assume that you've got equal and opposite charges. So this property, this is a consistent thing, this is always there. And the direction of it is in the direction, I'm going to call it r, because it's just sort of a general direction, but it's r from minus to plus. It's always pointing in that particular direction. And sometimes this value here, d, and the direction from negative to positive, we sometimes just call that the separation vector, d. In which case we can say that the dipole moment is related to Q, D, if you will.
So in this particular case,
this would be the electric dipole moment.
R is just positive y.
R would be up. It would be positive y direction, or positive j direction. So for our calculations, it would be Q, D, J for this particular problem. And if it's pointing in a different direction, then you just have to deal with it in terms of component flow. Yes?
So just to clarify, this will never have anything to do with anything outside of the dipole. It's just what's happening between the two particles that make up the dipole, or the two ends of the dipole.
Correct.
Okay.
However, there is one caveat to that. If you have two effective dipoles acting presently on the same system, then you can add them together and get a net electric dipole for the entire charged system. Example, water. Well, I'm going to erase this. This will be seen if the derivations in the textbook. So again, what are the advantages of this? Well, in the case of, say, for instance, water. Water has basically, it consists of two parts. It's got the spatial interaction, atomic interaction, molecular, excuse me, between a hydrogen and an oxygen, and then offset by a certain angle another hydrogen and oxygen. Well, because of the nature of these two different atomic entities, you tend to, when they are interacting and sharing their electrons, and this is important for protein formation, protein folding, anything that interacts with water in general, you end up getting, or anything that has hydrogen-oxygen interactions, you end up getting ever so subtle charge separations, where whatever electrons that are being shared to form this chemical bond are unevenly distributed. We call that a polar covalent bond, if you will. But the net result is that there's a dipole moment that points from negative to positive. So maybe we call this P1. And it's unfortunate we use P because now P is not the same thing as P for momentum. We should probably call it PD or PE, but it's what it is. And so that would be the direction of that dipole moment. Well, if you have another one associated with the same system, basically centered on the central oxygen molecule or atom, then you have a second dipole moment that would be pointing from the oxygen to the hydrogen. Should probably draw this a little closer here. When you add these together as vectors, x components cancel out and you're left with a net dipole moment that is the vector combination of the two. And if they were oriented in a different way, then, well, it would just be a different addition. They don't necessarily have to add or subtract. But the way molecules interact in electric fields will depend on their net electric dipole moment, which ultimately will be a combination of all the component dipole moments associated with that system in exactly the same way that multiple forces add to generate a net force. So that would be an example of it. But again, the assumption is equal and opposite charge separation. So in a physical system, it's rare that it's this charge and an equal and opposite charge just placed somewhere and secured. It's usually that you undergo some process or there's some reason why a net neutrally charged system will undo itself, organize in this dipolar or charge separation orientation. So that's essentially what it is. And I figured, you can get that out of the textbook because it's there. But I did want to point out the reason we use it, and the reason it's sort of advantageous for us, is that you see it, and this is a J, not an I, right? You see that thing in both places. So, I mean, it's common to the solution of the problem. In the same way that if you're looking at multiple charges affected by some separate charge, the one thing that stays the same is the magnitude of that disturbing charge and the 4 pi epsilon naught. And then everything else is just how far away you are. And if you're a set location, then even the space is common to the problem. So it's just a way of organizing and taking this thing out. And think about what this might mean if you had, for instance, this dipole, and assume that it was fixed. Okay, maybe this is a water molecule. Obviously it isn't, because I didn't use the right numbers. But what if this were a water molecule and it isn't necessarily two charges, but rather a net dipole moment of some value that could be measured in some way? If you were to place this in an electric field, in an external electric field, right? We calculated what this thing does. But ultimately, the real physics it comes into play when we say, okay, what is it when an electric field interacts with a charge or a charged system? Well, here's a net neutral charge system. But if you put an electric field in there, you're going to have two external electric field now, not its field, but something around it. You're going to get a net interaction away at the positive end and a net interaction toward at the negative end. Equal and opposite forces, but the generation of rotation and torque. Because this thing is going to twist. If it were fixed in place, or it's going to, who knows, if it's not fixed in place and has imparted with some initial motion. So this is a possibility. And that's why it tends to be of some advantage, because rather than having to go through all these calculations, if you can immediately get to that, just that starting point of this little electric dipole moment vector, how it interacts is oftentimes a more interesting and a broader physical concept, or mechanism, I should say, than just looking at an individual charge. Because functionally, that's probably more how proteins work. When proteins are affected by electrical changes, it's more likely that somewhere on that molecule there's a hydrogen-oxygen molecular bond, chemical bond, that is now being torqued, causing a protein to do something in a specific fashion. Nanotechnology will be based on using electric fields and dipole interactions in order to generate or design mechanisms for various microscopic applications. So it's very much a more useful concept, but it is really still based on just charge, how do they interact, got multiple charges, and deal with that as well. But it's kind of an important thing, and I've said a couple times, antennas are based on this idea, for instance. Okay, so any questions on how that fits together? It's heady stuff. I mean, it doesn't matter how I explain it. The first time you see it, you just sort of go through the calculation, or you look at it, you look at the result, you just sort of say something about it, and you just sort of, okay, yeah. But it takes time to digest, because this is highly technical. You finally get to use a little bit more of your calculus, and a little bit more of this deeper trigonometric relationships. But notice in both cases you have a cube of separation distance, inverse cube. Because of the positive and negative, and they're always usually working against each other, at least in one direction, the net consequence of that, or the consequence of that, is that the field that's generated by a dipole will dissipate much more quickly than just, say, an individual charge, for instance, Q. Because whatever the charge would be due to, say, the positive portion of this charge component, it'll ultimately be interfered with, and some aspect of it will be, in fact, opposed and canceled out by the negative that's there, too. So it ends up being these things rapidly diminish in their effect at distance much more quickly than just charges do. But it's just a Coulombic point charge particle application. Now, the next step to this, and I wanted to leave some time open, if you had to go to the restroom, you could. The next situation is, and it's a little bit artificial, but it's helpful. And that is, when you have charges. Now remember, all charges are discrete at some basic level. We're always talking about electrons there or not there in little points in space. However, that being said, if you have so many charges that it is very difficult to calculate the electric field, for instance, or for every individual charge, and therefore if you had some other charge, you've got a sweater and you've got some umpteen million electrons sitting on it, and you want to know the force on some electron out here, you don't want to do that calculation for every single charge. So we take the approach, if you've got a high enough density of a small enough localized charge, we can treat it as a charge distribution, a continuous charge system. Is it in an absolute sense? No. But if we can treat it as a continuous system, now we can apply some of the techniques that we've learned in calculus to in a more robust fashion to make problems a little bit easier to handle. And that's basically the next step in this process. And by the way, these problems are highly technical. They're the old phrase in physics, one of the physics majors, is the fundamental problem of physics is setting up the coordinate system so you can solve it in the first place. That ends up being the hardest part oftentimes. Statics the same way, dynamics, where you got some pulley doing this, and it's attached to something sliding, and mechanical, it's just getting the darn thing set up with related variables that are consistent is usually the hardest part. But the other thing is that in electrostatics, the hard part in a whole year of electrodynamics, even graduate level, would be mostly calculating the electric field and figuring out ways to calculate it. So again, once you know electric field, then all you have to do is stick a charge in and see what it does. But getting that electric field is almost always the hard part. So that ends up being the goal in most cases in the typical graduate physics class that addresses this topic. Okay, so the example that I put on the in the worksheet that I handed out is a simple situation where, and I probably should have made the charge a little bit lower instead of higher, because I think we're going to look at what happens above, is if you were to take the quintessential charged rod, I think that we used on last Friday, and add or remove some quantity of electric charge, whether it's a conducting rod or a insulating rod, the charges are going to try to put, well, I guess the insulating rod would be less the case. The charges, if they're free to move, are going to push it themselves as far away as possible from every other common electric charge. So the net result is, if you were to remove electrons from a, say, a bar, a conducting bar, then what would happen is that the electrons that were remaining would arrange themselves in such a way that it would appear as though you have a uniform positive charge along this rod. Now, the reality is, if you look close enough, maybe not. But because of the localized nature and the high density nature of these electric charges, it's close enough for government work. Now, once we have that, say for instance, it doesn't matter where I am, I want to know what the electric field is up here at, say, some point P. Well, what is it that I need to do? The problem is always this Coulomb law problem, where you divide out the charge that would ostensibly interact with that electric field. So, if I want to know what the electric field is, I could do one of two things. I could either look at the missing electron at a particular point in space, figure out its electric field over there, do the same thing to its neighbor, add that component of the electric field, and do that for every single missing electron along this thing, and physically just brute force, use a spreadsheet with 10 to the 23rd little rows, and then add them all up in X and Y and calculate it. Or I could take the elegant calculus approach, which is to say, if this is a continuous rod with some total Q, and I want to know what the electric field is at some distance away. And in this case, that distance away, I think we just say it's Y. It's just directly up. It can be in the center or not. We'll just assume that it's in the center. And if this rod has a total length of L, then maybe the easy approach is to break up this thing into tiny little chunks. And let's call each chunk dq. Well, if each chunk of charge that I choose to just hypothetically break this thing or chop this rod into, then up here, the electric field, I'm going to call it dE, because it's just the component of the field, or just the electric field due to this little charge alone. That would be equal to the amount of charge, which is now, I'm defining it as dQ, divided by 4 pi epsilon naught distance of separation squared of that particular charge, pointing in the direction, generically speaking, of R. In other words, along that line of action. Well, if I were to look at a different charge dq, unfortunately the angles and everything are going to change, separation distance, the whole schlemiel. So we got to then look at how, for instance, dq is related to the total q, because ultimately that's what I'm concerned with. And what we can recognize, and if I want to know what the total charge is, it's going to be equal to the sum of all of these little components of charge that I have. And so then the question is, given the nature of the system, is there a way to make this simplified? Well, if I've got a nice perpendicular type of system, maybe the best approach is to call the center along this direction the origin, and define a coordinate system, maybe y and x, in this fashion. In which case, as long as the rod is thin relative to the dimensions that I'm looking, I can define dq, or the unit of charge in this little quantity, as the total charge, as the density of charge. The amount of charge in this little region would basically be the charge per unit length along this whole thing times this little segment of length. In other words, if this thing is uniformly spread out, the charge is uniformly spread out, and I can say the charge density, Q total, divided by L, will be a constant quantity. In other words, if this thing's a meter long and there's a coulomb of charge, then you've got at any given, along this thing, you've got a charge per unit length of however many charges divided by the 1 meter. If this is the case, then any little charge dq will be related to the effective charge density of this system times, well, I conveniently gave myself a direction of orientation. And I'm basically saying that if I take a little chunk of slab dx, I multiply that length by the charge per unit length, that will give you the dq charge in that little square, in that little region. So now we have a way of expressing dq. So now as we just sort of extend this, dq then, we can write as dx times some constant uniform charge density, linear charge density, times epsilon naught r squared in some varying r direction, depending on which little chunk of dq I'm looking at. So if I wanted to know what the total electric field would be, I would take lambda dx, or let me say it this way, I would take the electric field associated with every little chunk dq, and I would add them all up. And each electric field component would be related to lambda dx over 4 pi epsilon naught r squared, pointing in the direction of r. Now we got a little bit of a problem here. If I want to evaluate this, r is not constant, nor is the direction r, the unit vector r. So the remainder of the problem is figuring out how to orient this thing in such a way that is useful so that I can evaluate an integral like this. Ultimately, if my dx's, dq's, excuse me, are lined up along the direction of the rod, and this rod is a length of L, and I'm calling my origin halfway in between, then really what I'm evaluating is I'm evaluating the electric field as I go from one end of the rod to the other for each of these tiny little charges. Rather than add them up individually, I'll take the calculus approach so that I can figure out a way to mass process the information. That's one of the things that the calculus does. It allows us to mass process what would be a discrete calculation nightmare. So then, the question is, well, what do we do with this? For each component dq. Now the nice thing is lambda, 4 pi epsilon naught, that's all constant, so that comes out. But we have to deal with two parts then. Well, here's my integral. I'm going to evaluate dx from minus L to L, or L over 2 to L, positive L over 2. Now I'm evaluating with respect to dx. So as I step along here, and I look at any particular direction r, as I'm at a different location along the x direction, location on the plane, my r is going to change, but it will still be related, or it will be related, I should say, to where it is relative to the origin, and also to the fixed distance away from the rod itself. So I can rewrite my r squared, if you will, as x squared, where x would be the distance of location where my dq is located. All right, dq is at a particular location x along the rod. If I add that to y squared, which is the separation distance here between the two, if this is a right triangle, x squared to this position plus y squared, the separation distance, or the distance away from the rod, that's going to be equal to r squared. So I don't have to take a square root and square it again. I just know it's going to be x squared plus y squared. Now the question becomes, what do I do with this r value? I need to convert this r into x and y components. Well, probably the easiest thing to do is define an angle, maybe we call it theta. And that angle will be related to the hypotenuse, or the absolute direction, to this charge, the charge that I'm looking at individually. And either the x position away from the origin or the y position away, depending on whether I'm looking at the x or the y component. X or y component, I should say. So here's my point above. I'm going to have, with my r vector, here's my angle theta. My electric field, if this is a positive charge, will be pointing outward at some angle directly from that dq. The angle with respect to the x-axis will be the same as the inner angle from the origin subtended toward the x. No? I'm looking at the wrong side, aren't I? It'll be this angle. Excuse me. Thank you. Opposite angle. So if I can define this angle in a useful way, I can calculate the x component, or if you will, the dex, and the dey component at that particular location, based on the orientation of the angle, and using something to do with the dimensions. It always comes back to the dimensions involved with the system running down. It's hard to integrate an x when your theta is changing, so your x, everything, your orientation of your vectors changes because of where you are in alignment to the point of interest or question. So if I want the x component, it would be related to the sine of this angle. Would be related to the magnitude dE times the sine of whatever that angle is in the I direction, and DE times the cosine of that same angle in the J direction. This would be how I could break apart the electric field, just solely to that little charge dq. Well, we've dealt with dE. That's based on this stuff here. The sine and the cosine then, we can express in terms of the dimensions of the system itself. Cosine of this angle, and we start with the cosine, start with the sine. The sine of this angle, expressed in terms of x as we move along, and y, would be related to wherever this charge is located along x, divided by, if you will, the square root of x squared plus y squared. By doing that, I've got a function, at least in the x direction, that has the integral, or the integratable integrand variable x. So I could write this as x square root of x squared plus y squared. That would be in the I direction. To figure out the y or the j direction, I just use the complementary trig function, which would be y divided by the square root of x squared plus y squared. Okay, so this would be the whole problem in its most horrible, longest form. Ultimately, we have to evaluate it both in I and J, because the net effect of all of these vectors, or of all of these charges, will have a net consequence, vector addition, vector sum in X and in Y, or I and J, if you will. So, extending this then, what I'm left with would be lambda over 4 pi epsilon naught, and I'm going to put my bracket outside, because now I'm going to have integration component that is from negative L over 2 to L over 2, each end of the rod, and it's going to be x dx divided by x squared plus y squared to the 3 halves, and that's in the I direction.